This is video 4 for the linear motion unit. So going back to Galileo, Galileo developed the concept of acceleration through his experiments on inclined planes. Now, his main interest was falling objects. Remember the Leaning Tower of Pisa. However, he lacked suitable timing devices. It's really hard to measure how many seconds it takes something to fall. Acceleration due to gravity is such a large value that after a couple of seconds, an object's fallen a great distance, really. So, to slow the object down, he used ramps. So imagine, taking a ramp and then making it steeper and steeper and steeper. Eventually, once the ramp is vertical, the object's in free fall. But before it gets to free fall, it's still accelerating along a ramp. So, what Galileo found was that the ball rolling down an incline will pick up the same amount of speed in successive seconds. So here's how he tested that out. He put bells on his ramp. And he spaced them out in such a way that as the ball would roll, it'd ring the bell once per second. So initially the ball was rolling slowly, so the bells could be closer together because it was moving slowly, it wasn't covering very much distance. But as the ball picked up speed, the bells had to be spread further and further apart in order to keep that successive second. So the ball would roll with unchanging acceleration, and that's something that he discovered. Since faster moving objects covered more ground, the bells can be placed at certain positions with the distance between them getting greater. And if you choose the correct positions of the bells, the ball would hit a bell each second. Now, we can then see that the instantaneous speed, or the velocity of a ball at any given time being released, is simply its acceleration multiplied by its time. So that Galileo found that with he would get greater accelerations for steeper inclines. And that the ball would attain its maximum acceleration when the incline was tipped vertically, regardless of the weight or size. So Galileo discovered that when air resistance is small, so that we can ignore it, all materials will fall at the same unchanging acceleration. So that leads us into free fall. So things fall because there's a force due to gravity acting on them. So when a falling object is free of all restraints, that means no friction, no air resistance, and falls under the influence of gravity alone, we consider that object to be in a state of free fall. So just to get some numbers up here, when 0 seconds have passed, the object has a velocity of 0, and we might imagine that. And so this time is in seconds. This velocity is in meters per second. After 1 second, the object would now be moving at 10 meters per second. So looking at these numbers then, we should see a pattern forming. We should see that it is the time multiplied by the number 10. And that's important because that number 10 is actually the acceleration due to gravity. So this should look like the formula above, where we have the acceleration multiplied by time equals the velocity. So the acceleration of a falling object, which we call g, is 10 meters per second per second. If you wanted to, you could write that unit as meters per second squared, but I kind of prefer this one. It lets you know that it's a changing velocity with respect to time. So, in the case of falling objects, we customarily use the letter g to represent the acceleration. That's because it's true for everything. G will vary slightly on different parts of the world. On average, it's 9.8 meters per second squared. I kind of like to round it off to 10 just to make the math easier. So then, the instantaneous velocity of a falling object is g times t. So that's something you need to know for your learning goals. Now we've been considering objects moving straight down in the direction of gravity. What about something that's being thrown straight up? Well, once it's released, it continues to move upward for a while, then comes back down. At its highest point, when it is changing its direction of motion from up to down, its instantaneous speed will be 0. Then, if it starts downward, just as if it was dropped from rest from that height. During the upward part, the object slows from its initial velocity to 0, and then from the downward part, it will increase. Now, there is symmetry in nature, so it shouldn't come as any surprise that the speed decreases by a rate of 10 meters per second every second. The same as the acceleration it would experience on the way down. So let's take a look at an example here. This is a person throwing a ball, person standing on a building, and the location of the ball represents 1 second. So we're going to say that at 0 seconds, this ball has an initial velocity of 30 meters per second, and it has an acceleration of negative 10 meters per second squared. So up here at 1 second, the ball will now have a velocity of 20 meters per second and an acceleration still of negative 10 meters per second squared. At 2 seconds, the ball now has a velocity of 10 meters per second and an acceleration of negative 10 meters per second squared. Notice the acceleration is staying the same. At 3 seconds, the ball now has a velocity of 0 meters per second. Now, pay attention to this part. A lot of people will say then, well, since the velocity is 0, the acceleration must be 0 as well. That's not the case. It is still negative 10 meters per second squared. Acceleration is defined as a changing velocity. If the acceleration is 0, then the velocity doesn't change. So if the acceleration were 0 up there at 3 seconds, that means that the object would not change its velocity of 0. It would have a constant velocity of 0. In other words, it would hover up there. So it's a very, very common misconception, but a lot of people think that when the velocity is 0, the acceleration is 0. That is not the case. Okay, coming back down here at 4 seconds, the ball now has a velocity of negative 10 meters per second, an acceleration of negative 10 meters per second squared. At 5 seconds, it now has a velocity of negative 20 meters per second, acceleration. 6 seconds, negative 30. And notice we have symmetry. Just, up is positive, down is negative. So since these are velocities, that's why I've been giving negatives, because it indicates direction. And there we have it, 7 seconds. But we do get some nice symmetry. The next question we may want to ask ourselves is how far? As an object is falling, how far does it travel? And this is something that Galileo found. Galileo found that an accelerating object, the distance it travels, is proportional to the square of the time. So, for time, measured in seconds, and distance measured in meters, he found that at 0 seconds, it will travel 0 meters, and that should be expected. After 1 second, it will travel 5 meters. 2 seconds, 20. 3 seconds, 4 seconds, 5 seconds. again, these are meters. There's roughly 3 feet to a meter. So after 1 second, it's traveled roughly 15 feet. That's like a story and a half of a building. After 2 seconds, like 60 feet. That's like a 6-story building. So it's the distances add up very, very, very quickly. So looking at these numbers, we can get a model or a formula that says that the distance it travels equals 1/2 g t squared. So, when you get a second, plug in some of those numbers and see if they work out. If I plug in 3 seconds, well, 3 squared is 9. 9 times 10 is 90, and then half of 90 is 45. So that works out. And you can do that with any of those numbers. Now, one last thing I want to leave you with. Notice then that the ball only goes a displacement of 5 meters during the first second. Its speed at 1 second would be 10 meters per second. This may be confusing. We think that if an object travels at a speed of 10 meters per second, then it should travel 10 meters in 1 second. But keep in mind, for it to fall 10 meters in the first second, it would have to have an average speed of 10 meters per second for that entire second. However, this thing, it started from rest, and it only reached 10 meters per second at that last instant, that last part of that second. So if we think about it, its average speed would be 0 plus 10 divided by 2. It would be 5 meters per second for the first second of travel. Then that kind of makes sense that, oh, well, if its average speed is 5 meters per second, it would travel 5 meters. So, just one thing to think about. This is something that can be confusing for students, but if you really understand the difference between average and instantaneous speeds, then this should make some sense. Well, that concludes this unit.